Sometimes a single number just doesn't cut it. If I tell you to walk 5 kilometers, you're missing a pretty crucial piece of information, right? Which way? Well, that's where vectors come in. They're this amazing mathematical tool that tells us not just how much, but also where to. All right, so here's our game plan for today. We're going to start with what a vector even is, then learn how to speak their language. After that, we'll get into the fun stuff, the math we can do with them, and then see how all of this helps us navigate grids and solve some really cool geometric puzzles. So let's start at the very beginning. What exactly is a vector? And why is it so important? Think about it. If you're giving someone directions, you can't just say, go 2 miles. That could be 2 miles north, south, east, west, literally anywhere in a circle. The distance by itself is useless. You absolutely need something more.
And that something more is a vector. This is the big idea right here. A vector is a quantity that bundles two critical pieces of information together, a size, which we call its magnitude, and a direction. It answers both how far and which way all at once.
This slide breaks down that difference perfectly. A simple number, what we call a scalar, is just about size, like your speed, 60 miles per hour. But your velocity, that's a vector. It's 60 miles per hour due north. See the difference? Same goes for mass versus the force of gravity pulling on it. One's a scalar, the other's a vector. And get this, the word itself is a huge clue. Vector comes from the Latin for carrier, and that's exactly what it does. It carries you from a starting point to an ending point. It describes a journey, a translation from A to B. Okay, so we've got the concept down. Now, how do we actually work with these things? Let's dive into the language of vectors, how we draw them, write them, and make sense of them. Visually, it's super simple. A vector is just an arrow. The longer the arrow, the bigger the size. And the arrowhead, well, that points you in the right direction. When we write them, we can use a bold letter or underline it if we're writing by hand. Or we can be really specific and describe the journey from point A to point B. But for doing any real math, we need something more precise. And this is where the column vector comes in. Honestly, this is a game changer. It's a super clean way to capture that whole journey with just 2 simple numbers. It's fundamental to things like physics engines and computer graphics. Okay, here's how to read it. It's way easier than it looks. The top number is your side-to-side movement. Positive means go right, negative means go left. The bottom number is your up and down. Positive for up, negative for down. So that example, 3/4, is just a recipe. Go 3 steps to the right and 4 steps up. That's it. So we can write them down, which is great. But what can we actually do with them? Well, this is where vectors get their superpowers. Let's talk about vector arithmetic. First off, we can stretch them and shrink them. If you take a vector, let's call it A, and multiply it by a simple number like 2, you get a new vector, 2A. It's twice as long, but points in the exact same direction. And if you multiply it by a negative number like -1, you get -A, which is the same length but flips around to point in the completely opposite direction. We can also add them together. The best way to think about this is like following a map. If vector A is the journey from your house to the store, and vector B is the journey from the store to the park, then the new vector A plus B is the single direct path from your house straight to the park. You just draw one arrow after the other, head to tail. And here's a neat little trick. Subtraction isn't even a new thing. To subtract vector B, you just add its negative. So you take that first journey A, and then you just follow it up with the reverse journey of B. It's just a special kind of addition. Now this is why column vectors are so amazing. All that visual head-to-tail stuff, it becomes incredibly simple arithmetic. To multiply by a number, like in that first example, you just multiply each part inside the vector. To add or subtract, you just combine the top numbers together and then the bottom numbers together. It's so clean and straightforward. All right, theory's great, but let's put these new skills to the test. This is the payoff, folks. We're going to use what we just learned to find our way around a grid. Okay, check out this diagram. We're given these 2 basic paths, vector A and vector B. The puzzle is, how do we describe the journey from point F all the way to point B using only those 2 vectors? How would you do it? Well, we can't go directly, but we can piece together a path we do know. To get from F to B, a clever route is to first go from F to A and then from A to B. Now, that trip from F to A is the exact opposite of vector B, right? So we call that negative b. And the trip from A to B is just good old vector A. And now we just add those two parts of the journey together, negative b plus a. We can write that a little more neatly as a minus b. And just like that, we've used simple vector math to describe a complex path. How cool is that? Okay, so we can navigate. Let's level up. This is where we unlock the real secret power of vectors, proving things about geometry that would be a huge headache otherwise. This is the kind of stuff that makes vectors absolutely essential. And it all comes down to two surprisingly simple rules. Rule number 1, parallel vectors. If you can show that one vector is just a scaled-up version of another, like, say, the journey from C to D is exactly 3 times the journey from A to B, then bam, you've proven they're parallel. Rule number 2 builds on that. To prove 3 points are on the same line, all you have to do is show the journey from A to B is parallel to the journey from A to C. Think about it this way. If the path from A to B points in the exact same direction as the path from A to C, and they both start at the same point, A, well, they have to be on the same straight line, right? There's nowhere else for them to go. It's such an elegant way to prove it. So what's the big takeaway? This vector toolkit isn't just for describing where things are. It's for proving, with mathematical certainty, facts about shapes, lines, and points. We can use this clean algebra to solve some really tricky geometric problems. So, everything we've done today has been on a flat two-dimensional plane. Right, left, up, down. But hold on. Our world isn't flat, is it? So here's something to chew on. What do you think happens when we add a third number to our column vector? A z component. Where does that new journey take us?